Okay, so now the next thing is the following object called the identity matrix. Oops. Okay, so it's just some matrix IN, which is called the n by n identity matrix is the matrix whose entries are given by in of ij. The ij's entry is either 0 if I not equal to j, or 1 if I equal to j. All right. So, to put it differently, if we try to write the whole thing, you'll be looking at this matrix 1, 0 everywhere else, 0, 1, 0 everywhere else, 0, 0, 1, 0, 0, and down to here, finally a 1. Okay, so if you look at it closely, and the condition, as you can see here, is that the ij's entry is 1 if I is equal to j, and 0 otherwise. Having I equal to j means that the entry you're looking at is on this diagonal. So, in other words, being that the identity matrix is the matrix whose entries on the diagonal are 1, and all other entries are 0. Okay, so for example, I2 is the 2 by 2 identity matrix, this one. I3 is the 3 by 3 identity matrix, that is this one. Okay, now property. The word identity matrix is, identity for something, right? IN is the multiplicative identity for n by n matrices. That's essentially the reason for considering the identity matrix. And what this means, being multiplicative identity, means that for i.e. for any a, and n by n matrix, we have a times in equals to a, in times a equals to a. Okay. Now this, in fact, is a bit more general. More generally, if B, say, is a P by Q matrix, then the following holds. B I Q is B, I P B is B. Now, oops, Now this here, this is P by Q, the matrix B. IQ is the Q by Q identity matrix, so it's Q by Q. And the product is P by Q, so it's possible that it's equal to B. And my claim is that it is equal to B. Similarly, the IP is the P by P identity matrix. B is the P by Q matrix, so the product IPB is size P by Q. Okay. Now, all right, so that's what the identity matrix is. Now the next thing to mention is the following. As you recall, suppose we have two vectors in Rn, u1, u2, un, v1, v being v1, v2, vn, vectors or n-dimensional vectors. Okay. Now for any two n-dimensional vectors like these, we have the scalar or dot product u dot v being defined to be u1 v1 plus u2 v2 up to u and vn. Right, this is a number. Now, there's an easy observation to make. That is the following. First of all, we can view U and V as n by 1 matrices. Then we have the following equality. Okay, you can, if U is considered n by 1 matrix, then you can take its transpose. This becomes a 1 by n matrix. Then you can matrix multiply with V, because V is an n by 1 matrix, right? So the outcome of this matrix product is a 1 by 1 matrix, that is a number. Which number? We are going to find out now. U transpose, first of all, is a 1 by n matrix, so it's a row like that. And V is still V. Now, if you are taking the matrix product of these two, you'll be taking this row multiplied by this column in the way the matrix product is defined, namely multiply the corresponding entries together, then add them. And this is, as we've seen already, what U dot V is. So in other words, U dot V here, the scalar product or the dot product, can be interpreted as a matrix multiplication, U transpose times V. Okay. And now, also recall in R2, you have R2 points on the plane corresponding to pairs, right? On the plane pairs. So for example, let's say we draw the usual XY plane, and here is the origin, and suppose you have a point here called P, and this point corresponding to a pair, say AB. Then let me extend this a little. Okay, and then the distance between O and the distance between the origin and the point P, or the length of the interval or the line segment OP here is computed as follows, right? So first of all, this projection here, this is A. This projection is B. That's how the coordinates or the points are supposed to work. So that means this length is A and this length is B. So by the Pythagorean theorem, the length of the line segment OP is the square root of A squared plus B squared. Okay. And this length, I mean, we should also think of it as the length of the vector going from O to P. And this is also true in higher dimension. In higher dimension, the length, of the vector, say this one, x1, x2, xn, is, first of all, it is this quantity, the square root of the sum of squares of the entries. And secondly, let's introduce a notation for this. So this is the length. This quantity here, this expression gives you the length of the vector x. It has a different name as well. It's called norm. Okay. Now, of course, using the observation we just had about dot products and the matrix multiplication, this is also equal to the square root of x transpose times x. Okay, now, furthermore, for vectors, if you have two vectors, x and y, in Rn, not R2, the distance between them is given by the norm of their difference. So that is x1 minus y1 square, x2 minus y2 square, xn minus yn square. Okay. Okay, so this tells you how to compute the distance between two vectors. Maybe I should correct this a little. The distance. Now, for example, let's say you have two vectors in R3. Let's give them names, maybe. Then the norm or length of x is the sum of squares, which is 9, 10, 14. The length of y is also 14, square root of 14. The distance between x and y is minus 2 minus 1 square, 3 minus 2 square, 1 minus 3 square. So that is 3 square, 1 square, 2 square, no, still 14. Okay. Okay. So now we proceed to the next topic. This is about linear dependence. Okay, so you can recall that if we have an n by n system, we have several ways of writing it. Yep. Right, the standard way was a1x1, a12 x2, a1n xn equals b1, down to am1 x1, am2 x2, amn xn, bn, like that. And we've used matrix multiplication to write the system as ax equals to b, where A is the coefficient matrix aij, x is the column vector x1 through xn, b is the column vector b1 through bm. Oops. Right. Okay. It can also be written as follows. Right. Remember, one way of thinking about a matrix is to think of it as the collection of its columns. So we do that. This A1, A2 through AN, these are the columns. Okay. Then AX. As you know, AX is a n by 1 matrix, right? Because A is n by n, X is n by 1. So AX is an n by 1 matrix. This is written as a vector. N by 1 matrix is a m-dimensional vector. And which vector this is, is the following. If you follow through the definition of matrix multiplication, you see that AX is actually equal to x1a1 plus x2a2 all the way up to xn an. Okay, so we consider something like this. What is something like this? You have a bunch of vectors, each of which carries a multiple, and then you add up the result. Such a thing is called a linear combination of the vectors a1, a2, an. Okay, and the linear system can be written as, therefore, this linear combination equaling B. Okay, that's a different way of thinking about linear systems. Now for homogeneous systems, if the system is actually homogeneous, we have all the b's equal to 0. So the vector B is given by a column vector of zeros like that. Okay, and we denote a column vector of all whose entries are all 0 by a 0. So a homogeneous system can be written as x1 a1 plus x2 a2 plus xn an equaling 0. Okay. Maybe I want it differently. Okay, so this is a different way of writing a homogeneous system. Now, what this equation means is on one hand you have linear combination of vectors a1 through an, and on the other hand you have the 0 vector. And you're asking when this can happen. And certainly, a homogeneous system always has the zero solution. Namely, all the variables x1 through xn are equal to 0. Okay. There are two possibilities, right? Either a homogeneous system either has only the zero solution, or it has non-zero solutions. In case it has non-zero solutions, it has infinite many solutions. So you can interpret these two possibilities as saying that the first possibility is saying that the only linear combination of a1 through an to equal to the zero vector is the trivial one, namely having all the x's being 0. And the other possibility would be there are infinitely many non-trivial ways of making the linear combination of a1 through an equal to the zero vector. Okay, and this leads to the following definition. Now, suppose V1, V2, Vp are m-dimensional vectors. Okay. Then V1, V2, Vp are what we call linearly independent. If the only possible A1 through AP making the equation A1 V1 plus A2 V2 plus up to AP VP equal to zero vector, making this whole is A1 equal to 0, A2 equal to 0, and up to AP equal to 0. Okay. V1, V2 up to VP are linearly dependent if they are not linearly independent. Okay. So again, what are we doing here? We introduce the concept of linear independence or linear dependence. It's a concept applied to a collection of vectors, say V1 through Vp. And to decide whether they are linearly independent or not, what you do is you consider linear combinations of V1 through Vp and ask when a linear combination of these vectors can equal to the zero vector. Okay. If that happens only when the numbers A1 through AP are zero, then the vectors are linearly independent. If there are other possibilities of A1 through AP for this linear combination to equal to the zero vector, then the vectors V1 through Vp are linearly dependent. Okay. Now, for convenience, I should introduce a name for these A's. What we have, this A1 V1 through AP Vp is a linear combination of V1 through Vp. Now these A's are called coefficients. A1 through AP. Okay. Coefficients. Okay. Now, yes, now let's think about this. In some examples. Okay, say V1 is 1, 2, 3. V2 is 2 minus 1, 4. V3 is 0, 5, 2. So the question is, are they linearly independent or dependent? Okay. So what do we do? To decide on that, we have to consider linear combinations of these vectors. We need to decide, we need to find the values of these, of the x's, to find values of x1, x2, x3 for this to hold. If we can only, and we certainly know that having all the x's equal to 0 will make this equation true. If we find more than that, then we know the vectors are linearly dependent. Otherwise, they are linearly independent. So now what is this equation? This is an equation of vectors. The vectors being v1, v2, and v3, and they are these guys. Okay, so this is the equation, and just like what we discussed before, this is a way of writing a linear system. In fact, a homogeneous linear system. This is, oops. This is a homogeneous system with augmented matrix being the following: 1, 2, 3, 2 minus 1, 4, 0, 5, 2, 0, 0, 0. Okay. And finding all the possible values of x's among to solving this system. So that's what we need to do. And let me omit the process and get right to the answer. As you recall, the way to solve the system is to perform row operations to get the matrix into reduced echelon form. And that reduced echelon form reads as follows. Okay. So what does that tell us? That tells us that, again, the leading ones are here and there. They correspond to x1. Yeah. Something happened and I lost my page. Never mind. Can I undo whatever I did? Not sure what happened, but that's okay. I think we just lost the page I wrote. We'll go back to reproduce it again. So the linear system in question has augmented matrix 1, 2, 3, 2, minus 1, 4, 0, 5, 2, 0, 0, 0, gets transformed into reduced row echelon form. Okay. Now reading off the leading ones will give us the following. So it's it's x1 plus 2x3 equal to 0, x2 minus x3 equal to 0, x3 is x3. So the solutions are x1 equals to minus 2x3, x2 equals to x3, x3 is equal to x3. So the point here is that these two variables, x1 and x2, are dependent variables. Now they depend on x3, and x3 is free, so it has infinitely many solutions. Okay, now going back to what we talked about, right? If you have infinitely many solutions, that is, it means that you have infinitely many different linear combinations of v1, v2, and v3 equal to the zero vector. So they are linearly dependent. Okay, that's one example. So furthermore, we can write one such linear combination of v1, v2, v3 that equals the zero vector. And this is it. Okay. That's an example. Now another example would be, let's say, the following. V1, 1, 2, minus 3. V2, minus 2, 1, 1. V3, 1, minus 1, minus 2. Okay, and again, the question is whether it is linearly independent or dependent. Okay, and again, that amounts to consider the following linear equation of vectors, which is the following linear system. Again, you see that you have a homogeneous system with augmented matrix given as follows. One, 2, minus 3, minus 2, 1, 1, 1, minus 1, minus 2, 0, 0, 0 here. Now, you can again solve the system by running row operations to turn the augmented matrix into reduced row echelon form. In this case, the answer is like this. So you can see that the corresponding system now becomes x1 equals to 0, x2 equals to 0, x3 equals to 0. So it has only the 0 solution. And what does that mean? That means there's only one linear combination of the v's that's equal to the 0 vector, namely the ones with coefficients being 0. So these vectors are linearly independent. Okay. Very good. Now, let's proceed to introduce some useful things. So first of all, there's a definition. In the n-dimensional space Rn, we have the following called unit vectors. And they are denoted by E1 through En. E1 is the one whose first entry is a 1 and all other entries are 0. E2 is the one with second entry 1 and other entries 0. Likewise, EI Here's the one whose ith entry is 1, other entries are 0. And finally, let's not do that again. And finally, En is the one whose nth entry is 1 and other entries at 0. Yeah. These are all n-dimensional vectors. And they certainly look very special, right? They're very simple for one thing, because their entries are all 0 except for 1. Now the first observation is that E1 through En are linearly independent. And that is easily seen because you just follow the definition by considering the linear system or the linear combinations of E1 through En and set them to equal to the 0 vector and see what you get. This linear system here, or this equation here, is the linear system x1, x2, xn equals to 0. Right. And if you write this out, I mean, you don't even need to think very hard. If you just write this out as a single equation of vectors, what you get is this is x1. The left-hand side is the vector x1 through xn. The right-hand side is the 0 vector, so you immediately see that the only solution to this system is the 0 solution. And that means E1 through En are linearly independent. Now, another thing to notice is that every vector in Rn is a linear combination of E1 through En. And that's easy because if you have your vector A1 through An, all you have to do is write it as the following linear combination. Okay. Now, certainly, if you just once you know this, if you just compute the right-hand side, you'll see that's indeed equal to the left-hand side. But the right-hand side here, these vectors are E1 through En. So that's how it works. Okay, we will. Yeah. Okay, so lastly, let's consider a theorem. We've certainly seen that the way to decide whether the collection of vectors is linearly independent or not is to consider certain homogeneous system associated to them and decide whether they have infinite many solutions or only the trivial solution. Right? So in view of that, you can formulate the following theorem. So suppose these are vectors in Rm, say Rm, if P is bigger than M, then V1 through Vp are linearly dependent. Okay, that is if you have too many vectors, that is say, then they must be linearly dependent. The proof of this is rather easy. So what do? You consider XPVP. You consider the linear system, or rather the linear combination equaling of the V's equaling 0. And what? This is, and just notice that this is a homogeneous system with how many unknowns? With P unknowns. Yeah. And P unknowns being x1 through xp, right? And M equations. Right? Each vector is m dimensional, so that's m entries, and each entry will give you the equation. Now, we've seen before that if you have more unknowns, if you have fewer equations than you have unknowns, you have infinitely many solutions. Okay. So since P, the number of unknowns, is more than the number of equations, there are infinitely many solutions. Okay. So that's it. As an example, this is just telling you that, first of all, this theorem is just telling you that if you have more vectors than you have, then if you have more than m vectors in Rm, then they are linearly dependent. So for example, if you have two-dimensional vectors, if you have three two-dimensional vectors, whatever the three vectors are, they are linearly dependent. Okay, that's just how it is. All right, now we stop here.